We're going to talk about medium voltage VFDs, intelligent motor control, and the $50,000 mistake on $1 million projects. We're here at the old Battersea Power Station in London, where Energy Drive has its corporate headquarters. Medium voltage VFDs have been around for decades, but what we're seeing more and more of now is energy performance being enhanced and unlocked with intelligent motor control. This video follows on a talk that I did at AIS Tech in May, in which I unpacked 20 years experience working on fan, pump and compressed air systems, delivering energy savings between 30 and 80%. Our last system that we just commissioned is actually a fume extraction system on a steel plant that is delivering a consistent 60% energy reduction on 2 fans with VFDs. And for those of you like me who are into harmonics, we've got a couple of charts that'll unpack some of the fundamentals and some of the important principles about VFD installations. When we talk about intelligent motor control, what we're really doing is understanding the process requirements, what the system really needs, and then satisfying those process requirements with as little electrical energy coming into the system as possible. If we take a fume extraction system, let's say, we often come across those with partially closed dampers. If we were to open those dampers, reduce the losses associated with the dampers, slow down the fan, we can satisfy the same process requirements, but with less power coming into the motor. As we slow the fan down, the affinity laws apply. And what that basically means is that if we were to reduce the flow by 20%, we reduce the speed by 20%. A 20% speed reduction unlocks virtually a 50% power reduction, which is significant. What this means is that even a small adjustment in flow can unlock a very large adjustment in power. With the VFD's ability to control speed, we're also able to start up a motor more slowly. Very large fan impellers with a huge diameter and a massive rotating inertia are very difficult for motors to start. I've seen motors take 20 to 30 seconds to start these large diameter fans up, whereas with a VFD, we can do that slowly. We can take minutes to start the same fan. And what that does is it reduces the electrical inrush, it reduces the mechanical shock on the system, and a bunch of other benefits as well. The largest source of heat in an electric motor is due to your joule losses or I squared R losses. And as the name implies, it's the square of current that drives those losses. When we reduce the motor power, we reduce the motor current. As we reduce the motor current, given that that's squared, we make a dramatic reduction to the heat load inside that motor. So what does this mean? A cooler motor is going to oxidize its windings more slowly. And the rule of thumb is that for every 10 degrees temperature reduction, we've got an additional 20,000 hours on the lifespan of the motor insulation. This picture taken of me over 12 years ago was one of my first projects with the Energy Drive. We did 2.5 megawatt fans that were responsible for primary and secondary extraction out of a steel plant. With the process dampers in the plant changing positions, the flow was changing as well. We implemented speed control and were able to deliver a 55% energy reduction. What I really enjoyed about that project was being new at Energy Drive and new to the world of very large fans. I was able to stay late one night and play around with the speed of those fans, and we were able to start at really high speed and bring it all the way down and show that the power demand actually followed the affinity laws beautifully. And I was really happy to see that the theory actually played out exactly as expected, even on massive fans. I got to join my team in Spain on the final commissioning of a fume extraction system, this one actually producing 60% energy reduction. And I took these pictures of the output waveform. What I love about this picture is how smooth that waveform is, with a very, very low harmonic content. And it's impossible to dive into the detail of this in such a short clip. But the reality of it is less harmonics, less negative sequence harmonics. You don't have the backward spinning magnetic field inside the motor fighting the forward spinning fundamental field. Cooler motor, lower insulation temperature, better energy efficiency, and just a better system. And the VFD guys did this with a simple architecture. They solved a complex engineering challenge with architecture instead of complex electronics. So what did they do? They've got an input transformer, phase shifted and isolated secondaries. Those secondaries are each then connected to a power cell, a low voltage power cell, and those are connected in series. What does that mean? We're able to control the individual power cells, stack the voltages on top of each other, and instead of switching a large voltage, we can switch the voltage in smaller steps, which gives us that cleaner waveform. It's a beautiful sinusoidal wave, much kinder to electric motors. So if VFDs are a reliable, proven technology, why aren't we seeing them being deployed in the field? VFD projects can be complex. Taking the time to slow down and understand the process requirements and build the necessary controls. There's also a lot that goes into these projects in terms of switchgear, cabling, e-cabins, cooling systems, you name it. The next one would be risk. It's very easy to lose the energy performance benefits with just a small risk to production quality or production throughput. We at Energy Drive mitigate this largely by installing bypass systems. Should something go wrong with the VFD, we'll very quickly be able to return the plant back to its operation identical to before the VFD was installed. Effectively, we electrically remove the VFD and the plant continues to run as though we'd never been installed. So at Energy Drive, we take care of the complexity. We'll design, procure, build, install, and commission the system, and actually guarantee the energy performance over the lifetime of the system. In terms of cost, our solutions are CapEx free, and that last one, the $50,000 on metering, we install sealed, calibrated, certified energy meters, utility grade, that are able to accurately quantify the energy performance of the system. If you'd like to know more, just reach out. We can come and have a look at your systems and see what we can do together.